Okay, hello everybody and welcome to this workshop on knowledge graph embeddings. We're gonna wait for a few minutes, I would say 5 minutes, until everybody connects. We should also check for whether or not everything is set up properly. I'm gonna drop a Zoom link as well, so that you could ask questions in real time, because unfortunately the YouTube streaming has a delay of about 1 minute. So if you want to ask a question, do so in Zoom, and I'm going to drop a link right now. Also, type in the chat if you could hear me well, if everything is visible. Just let me know. Let me know if you experience any technical problems, but it should be set up. Oh, everything is tested and set up, so everything should be fine. Interestingly enough, the Zoom meeting that was working before is not working right now, so I'm going to make a new one. So let me know if you see the comments. Do you see this comment? I wonder if the chat also has a delay or not. Okay, we started a new Zoom meeting, so we should be set very shortly. Should be all set very shortly. Okay, we're gonna wait for a little bit longer so that people catch up, that everybody joins the beginning of the lecture, because it would be a little bit unfortunate if it so happens that many people skip or miss the beginning. So we're gonna wait for a little bit more. Monish, hello. So good to hear everything well. Is everything working? I'm gonna drop a Zoom link right now again. All right, so here's the link to the Zoom meeting. So I'm waiting for people to connect. Sounds good. We're gonna close the tablet for now. Prepare the presentation. All right. We have an assistant that's gonna poke me if there are questions in Zoom, so please do ask questions in Zoom or on YouTube. Amy, hello, happy to see you. And welcome to the workshop. Siobhan, sounds good. We're gonna start soon. Probably we should give it a few more minutes, so that more people find the link, more people join the workshop. And yes, please do join the Zoom meeting as well. That would be nice. We're gonna start soon. Oh, I hear myself. That's not good. All right, I see some people are in the Zoom meeting already. That is really nice. So we should have an instant chat there, so that is nice. Okay, I hear myself again. That is. And yes, please do join. That is a little bit confusing. Maybe somebody haven't muted themselves on Zoom. All right, let's make sure that everybody's muted on Zoom, so that I don't hear myself twice, especially if somebody is listening to the stream in through the loudspeakers, not the headphones. Maybe somebody. We're gonna wait a few more minutes. I would say so far, if you're listening already, let me know in Zoom what kind of background do you have. Do you know something about knowledge graph embeddings already? Do you know something about word embeddings? I would like to know who is here. I think we mostly have the AI club members so far, judging by the number of participants. So it's probably mostly mentors, but still, I would like to know. I would like to know who is there. So I'm gonna be waiting for your replies in the Zoom chat. We're gonna give it like 3 more minutes or so, and we're gonna start. So yeah, just feel free to type in the Zoom meeting, what is your background? Have you ever worked with word embeddings? Have you worked with knowledge graph embeddings, PyTorch, and things like that? All right. Okay. So, waiting for the chat replies. Nobody volunteered yet. Okay. You said I could type something. Go ahead. I know nothing. All right, let's start. I know nothing. I like that. That's I appreciate this information. It's actually really helpful to know, if you're not from this area. It's probably gonna be a little tricky because I do assume a little bit of background, but I'm gonna do my best to not assume too much. So, okay, let's jump into the presentation. So we're gonna be speaking about knowledge graph embeddings, and please do stop me or ask questions on Zoom if you're having any trouble. So if you have any questions, please do so. All right. So let's start by answering the question of what is a knowledge graph. So a knowledge graph is just a fancy word for some collection of facts that we have. I would say what is knowledge in general is a very deep philosophical question. We're not gonna even try to answer that. And so we're just formalizing things in a very simple way. So we're just saying that knowledge is a set of statements in a very specific form. So the form is E1 R E2. So this is essentially the nuclear element of knowledge. So E1 is entity 1, so something. R is a relation, and E2 is entity 2. So entity could be anything, and a relation could be many, many different things. So let's take a look at an example. So for example, if entity 1 is an apple, and if we're speaking about this particular apple, relation could have the interpretation of has property, and E2 could be green. So if we're saying that the apple is green, then E1 is apple, relation is, and E2 is green. Or relation could be have property, and E2 could be eatable or tasty. So all those things are relational statements, and the knowledge graph is just a collection of such statements. It's called a graph because you could imagine if you have many entities like that, and some of them are connected with different links, it essentially is a structure of a graph. So I keep getting a notification from the messenger. I'm afraid you may hear it. Okay, hopefully. No, the messenger is not that easy to quit. Sorry, 1 second. Alright, well, let's hope it's not too loud. Alright, so there are a few examples of knowledge graphs. So one of them is ConceptNet. So ConceptNet is this crowdsourced database of common sense knowledge. So for example, it has facts like cats like milk. Milk is white, milk is liquid, and other things like that. And while it may seem very trivial for a human, actually this is an invaluable resource for machine learners, because it's not that easy to collect such a knowledge base, because it's so obvious to everybody that like people usually don't sit down and don't write obvious facts, like the facts that are obvious to everybody. And so it's really nice that somebody actually took the effort and tried to collect this kind of knowledge base in a crowdsourced manner. The downside of this ConceptNet database is that it's very noisy. Sometimes, some of the links don't make sense. So for example, there's a link that the cat is an antonym to a book. Like, why did that happen? I don't know. But yeah, they're just mistakes. Another database for common sense knowledge is the CYC. It's a more organized effort. This database is much more restricted, it's much smaller, and it's only partially available to general public. But for research purposes, you could submit a request and you could get it. And it's much more carefully designed. There are fewer contradictions. And more commonly, the databases or knowledge graphs actually contain factual knowledge. Something like Alfred Hitchcock was the main producer for the movie Psycho. Things like that. And so one of the famous ones is this DBpedia database. So it's a collection of facts based on Wikipedia. So as you can imagine, it's a huge database with a lot of relations, like conducted, produced, acted in, married, was president. So all of those are different relations, and there are also probably millions of entities for different people, different places, and things like that. So those databases could be very small, could be very large. The number of relations could be small. So for example, in ConceptNet, it's like 30 relations. In DBpedia, it's thousands at least, if not more. So it's a very flexible framework. And we're going to be speaking today about flexible ways of representing it. So let's try to approach a question of what is a knowledge base embedding. Before that, let's think about how to usually represent a knowledge base. So a traditional representation would just be a database. So you store those statements somewhere. Probably you index them in some way so that it's easy to access. You could search for specific things that have a certain property, etc., etc. What are the pros of this approach? So the first obvious benefit is that this kind of approach is exact. So if you ever made an entry to into your database saying that Alfred Hitchcock produced the movie Psycho, you can be sure that this entry stays there, nothing happens to it. Like it's not that the probability of this entry is going to be 95. This entry is there 100%, and you can have almost as many entries as you want. So this precision is nice. Also, it's fully interpretable, right? You could definitely know where everything is stored. If you want to check a specific fact, you could always do so. If you're not sure why the database returns a specific value, you could just check the entries manually and inspect the database Moreover, if the database gives you an error that you know, you could easily correct that. You could just rewrite the value that is being stored. Yeah, and you can override this value, update your database, and you're good. So you don't have this error that you identified anymore. That being said, there are, of course, downsides. And firstly, it is data hungry in a way. So imagine if you have 1,000 entities and each entity could be connected to each entity. So if we imagine that the number of connections for an entity is proportional to the number of other entities that are there, which is, I think, a reasonable assumption, then in general, the storage is going to be quadratic in the number of entities that you have. The storage requirement is going to grow quadratically as you grow the number of entities and possible relations between them. So while those databases can be huge and you could store it in a distributed manner, if you're trying to collect the database of everything in this world, you can run into problems. On top of that, and I think this is a more important limitation, it's impossible to generalize naturally. So, you know, if, for example, oh, actually, I have I have an example set up already. So let's say Alfred Hitchcock directed the movie Psycho, and you have a relation that says, a relation by the name directed, right? And so you have a triple, Alfred Hitchcock directed Psycho. And then you have a relation starred, like Anthony Perkins starred in Psycho. So it is natural to assume that if we were looking at the relation knows, that Anthony Hitchcock knows Anthony Perkins. But in a regular database, there's no natural way to add this link automatically. You'll have to write those kinds of rules yourself if you want to propagate your knowledge base and if you want to expand it somehow. So this is a very, very serious limitation, in my opinion. And so distributed representations to the rescue. So the distributed representations is something we're going to be speaking about today. And the pros is that this distributed representation, I know that probably if you never heard much about word embeddings or distributed representations in general, you don't know what it is, and we're going to speak about it today. I just want to give you, the motivation, why is it cool, and then we're going to look into how to do that, how to obtain those distributed representations. So they naturally correct mistakes, and moreover, they naturally generalize. So while the regular database would not add this link between Alfred Hitchcock and Anthony Perkins based on those other links, the distributed representation we're speaking about can actually manage to add this link even though it may be absent in the database. The representation is also compressed. It is linear in the number of entities, but it doesn't grow as we add more and more facts, which is really nice, because if we were speaking about huge databases, it actually can be beneficial. And what is also very important is that this kind of representations could be used in downstream tasks. So you could take this knowledge distilled into this knowledge graph embedding, and you could pass it to your neural network or something else that can then use this knowledge. And since it is encoded efficiently, and essentially using the same language as neural networks do, such representations could be reused in downstream tasks. For example, if you're speaking about natural language processing or something else like that. There are also cons, of course. There's no free lunch. So first of all, knowledge graph embeddings require training. So it implies that sometimes it can be slow. It also requires you to do some work. It's much more difficult to obtain knowledge graph embeddings than just to write down all the knowledge triples that you have. And it also may be difficult to manually correct or update specific entries. So if we come back to this example with Alfred Hitchcock and the movie that he directed, so essentially what happens is that it is natural to assume that Alfred Hitchcock knows Anthony Perkins. And most likely our distributed representation is going to pick up on this fact. If it knows that mostly directors know all of their actors, but it just so happened that Alfred Hitchcock doesn't know Anthony Perkins, our distributed representation is going to assume that it's just an omission, like a missing data point. At the same time, what if Alfred Hitchcock hired an assistant, and specifically on the days when Anthony Perkins was in the studio, Alfred Hitchcock was traveling somewhere else. And maybe he actually never met Anthony Perkins, and the absence of the entry in our database is not a mistake, but actually a fact. So those kinds of exceptions may be difficult to manually correct and maybe difficult to include in a knowledge base. That is just a limitation of this generalizable property of knowledge graph embeddings. And I would say it's just the other side of the coin. You can have both. Well, at least not with the methods we're going to be speaking about today. So how can we obtain such a representation? So that is really the key thing of today's talk and today's workshop. And if you stick with me, you'll get an answer by the end of today. Before that, though, I would like to review a simpler concept, that of word embeddings. So right now, I need a little bit of activity from you. So I would like to know who knows about word embeddings already and who doesn't. So if you heard something about word embeddings, please type plus in the Zoom chat. If you haven't heard anything about word embeddings, please type minus. Or if you heard something but forgot, please do so. I'm going to take a little bit of time to collect the feedback. I'm seeing 1 plus. Somebody heard something about, Rochelle, heard something about word embeddings. Probably from the time when I was rehearsing the talk with her. Yes. Okay, Wayland Lee heard nothing about word embeddings. That is good. All right, let's then just assume that there are people who are not familiar with this idea. And let's speak about word embeddings first. So word embeddings, it is a way to represent a vector in way to represent a word as an array of numbers, as opposed to using some other representations. So usually, let's say you have some kind of neural network that works with sentences, that works with words. So you need to feed a sentence into a neural network, right? You're feeding words one by one. So a naive approach would be to do the following. Let's say you have a vocabulary of 1,000 words or 10,000 words, 1,000,000 words, and every word just have an index. So the word mother could be the first, the word apple could be word number 1,000, etc., etc. So you're feeding some sentence to your neural network, and you're feeding them one number at a time. You're feeding like word number 1, word number 3, word number 100, etc. And so essentially the neural network, to understand what are you saying, the neural network is going to have to remember the meaning of every specific index. And the problem is that the closeness of indices doesn't mean anything to the neural network. So for example, the word number 1,000 could be a queen, and the word 1,001 could be a fire truck. And so the fact that those two numbers are close doesn't mean anything at all, and it's not informative. So the neural network would have to learn everything from scratch. That is not nice. So people, of course, realized that problem, and they wanted some kind of different representations. So if we represent words as vectors in a multidimensional space, we have this natural notion of similarity. So if we would like a word for mother to be closer to the word for dad than it is to the fire truck, and we would probably like the word for queen to be closer to a king than to a fire truck as well. So the idea is, I hope, clear. And this idea, like the way we implement this idea, is based on this distributional hypothesis of meaning. So the hypothesis states that words that appear in similar context share a similar meaning. So for example, if I have words cup and mug, you could imagine that I could say something, I took a mug and sipped from it, and I could also say I took a cup and sipped from it. And there are many situations where the cup and mug could be essentially interchanged. And that captures this idea that the cup and mug are similar in meaning. But at the same time, you could imagine that the word cup and a vase could also share some context. So for example, I could say I poured a little bit of water into a mug, and I poured a little bit of water into a vase, but I took a vase and sipped from it is a little weird. So you could imagine that the distribution of contexts in which the vase and a cup appear, they're different. And so it reflects the fact that the vase and a cup are more different in terms of what meaning they convey than a cup and a mug. And so if we take this idea, which is, by the way, it's not like universally accepted, it's just a hypothesis that's coming from theoretical linguistics, but it is a useful hypothesis, and we could actually formalize that. So we could formalize it and do the following. We could try to train word embeddings so that words that appear in different sentences, or sorry, in the same sentences, in same context, have similar vector representation. And similar is just, you could measure the cosine distance or something like this, and this way we're going to define similarity. So if we formalize this idea, if we train those vectors in such a way, we could obtain a vector for every specific word that we have, and they're going to be represented as vectors. So what is interesting about those word embeddings is that what we get while we're just training the vectors to be close if they appear more formally. Previously, we had a score, some kind of co-occurrence score for every pair of words. And this score represented how likely this pair of words was going to co-occur. So now when we're speaking about knowledge graph embeddings, we need a score for every triple. And this triple is the head, relation, and a tail. So, for example, Albert likes Maria, right? So we have three entities.
I don't know. Never mind. My internet was working, so I was just checking if there's.
Okay. Oh my God, there was some internet problem. Okay, that's not good. Let me check. Just give me 1 second. Let me know, guys. When did it cut out? What did you miss? Like, is it one slide, or is it something more substantial? Oh my God. All right, so we had some problems with internet. So apparently I had some. Oh my God, that's quite a lot. You were at slide 12. Okay, we're going back to slide 12 then. Which is quite a lot. All right. So we were speaking about the key idea of word embeddings. I think I was speaking for like 15 minutes or so.
Yeah, my internet went out, and I was like, I don't know, he's still talking, so I might have.
Okay. All right. Well, let's get back to business then. All right. So I was speaking about the key idea of word embeddings. So the index-based representation doesn't capture any useful information. So what it means is, if you're feeding just the indices of words to your neural network, you're not really helping it to figure out that a queen is not as is more similar to a king than it is to a fire track, because it may just happen that the index for the queen is like 1,000 and the index for a fire track is 1,001. So word embeddings try to capture, try to tackle this problem by instead of using indices that are, that lack individuality, they're using vectors that are very, very specific for every word and, specially tailored to capture the similarity in meaning, just as opposed to capture no specific information at all. So what we want is for the two vectors to be close in the multidimensional vector space if they share the same meaning. And while in general it's very difficult to define what meaning is, we're going to rely on this idea from theoretical linguistics, the idea of distributed hypothesis of, or distributional hypothesis of meaning. So the idea is that two words share a similar meaning if they appear in similar contexts. So essentially, if you think about a cup, the words for cup and a mug, you could imagine that those words are going to be used in very similar contexts. So I could say, I took a cup and sipped from it. I took a mug and sipped from it. So if you imagine all the contexts in which those words could occur, most likely many of them are going to be very, very similar. And this reflects the idea that the cup and the mug share the same or like a similar meaning. At the same time, if you think about a cup and a vase, there's still going to be some overlap in context, but some things are going to be a little bit unnatural. You wouldn't say, I was sipping my coffee from a vase. It's a little weird. And if you're so essentially the overlap is still going to be there, but it's not going to be full, not going to be as complete as between a cup and a mug. And this is going to reflect the idea that the cup and a mug are closer in meaning than the cup and a vase. And if we push this idea further, if you're thinking about a phrase something like I was holding my fire truck and sipping coffee from it, it becomes completely implausible that the fire truck would really occur in this context. And this reflects the idea that the fire truck has a completely different meaning from that of a cup. So this hypothesis is just a hypothesis. It is criticized, and you could probably come up with a few examples that show its limitations. But at the same time, it is useful and it's easy to formalize. And word embeddings do exactly that. They formalize this idea to obtain useful representations for word vectors. So we are going to be training, in case of word embeddings, we're training our word vectors to be close if the words occur in the same context. And while this sounds like a very simple idea, it leads to very surprising results. So it so happens if you train with this objective, you get certain interesting properties for free, such that most surprisingly perhaps is this naturally occurring vector algebra. So if you take a vector that connects a man to a woman, so essentially if you subtract a vector for the man from the king and you add a vector for a woman to whatever is left, you're getting something close to a queen. And similarly, you could find a vector that's going to connect the male and female versions of the same entity. And you could similarly obtain a vector that would connect the present and past tenses of a verb. So you could, for example, take the vector for walked, you could subtract walking from it, and then you could add this difference to the vector for swimming, and you could obtain something like swam. I must mention that recently there were some results that show that maybe not everything is all as clear-cut as was presented in the original papers that were advertising this result. But I would say it's still safe to say that there are wonderful properties that you do obtain. Maybe not all results when it comes to those vector arithmetic on word embeddings hold, but some of them do. And it is an interesting approach to obtaining interpretable, flexible representations. So I would like to clarify a little bit what I mean by sorry, one second. Well, hopefully no urgent messages anymore. That I hope the stream is still on and all that stuff. So I would like to clarify what I mean by optimizing things and by forcing the vectors to be close and all that. Because essentially it is very easy to formalize, and here's the objective function from one of the famous word embedding models. This is the objective function for the glove embeddings. So the key part of this function is here. Oh, by the way, I'm not presenting properly for some reason. So the key part of this function is underlined in red. Okay, just one second. All right. So this is one of the key parts of this formula, the one underlined in red. So what it says is that ui and vj are vectors for are vector representations for words I and j, and pij is the measure of the frequency of their co-occurrence. So the reason we're taking the logarithm has to do with how words are distributed. It is a technicality, but the key thing is that we just want vectors to be close because we're taking a dot product here, and dot product measures how close the vectors are. So essentially, we want this dot product to be high if the words co-occur often, and we want it to be low if the words don't co-occur too often. So this simple idea leads. So if we minimize this objective, we get those wonderful results we were speaking about before, which is, I think, impressive. So now the key is, how do we generalize this idea to the context of knowledge graph embeddings? Because the tricky part is that in case of word embeddings, we have one key entity we're kind of aiming to capture. It is co-occurrence. So we want vectors to be close if the words co-occur, and that is all. In case of knowledge graph embeddings, it's a little different. And the difference is that now words can co-occur in one context and words can be connected in one context, in the context of one relation, and they can be not connected at all in the context of another. So for example, let's say we have an entity Mary and an entity John, and they can be connected using the relation of likes. Mary likes John, but it's most likely that Mary is not going to hate John if she likes John. So they're not going to be connected via the relation of hates. So it seems that we need to somehow obtain a more flexible representation for every word, so that the vectors appear close in the context of one relation, and they don't appear close in the context of another relation. So more specifically, previously we were working with pairs, just pairs of words, and we want some score for every pair of how likely this pair of words is going to occur in a sentence. Now, when we're moving to knowledge graph embeddings, we're looking at triples, and we want a score for every triple that is going to answer us whether or not this statement holds. So the triple consists of a head, relation, and a tail. So Mary likes John, Mary is the head, relation is likes, and tail is John. So how do we generalize that, and how do we formalize this intuition? So let's take a look at one of the, I would say, older but also still relevant models for knowledge graph embeddings. It's called the Rescal model. I think it was introduced in 2014 or 15, so by today's measures it's a little bit outdated, but at the same time, most of the models that are relevant today, they stem from it in one way or another, and they're usually fairly simple extensions. So it's not, it's not like a jump from LSTM to transformers, or like it's not a jump from a steam engine to nuclear fuel. It's more like a jump from one steam engine to a slightly modified version of another version of a steam engine. So if you want to dig deeper into this field, you're going to be able to do so, provided that you understand the basic machinery. Also, what is interesting is that in many areas of machine learning, the development went towards more complicated models, more powerful models. In case of word embeddings, this Rescal is actually one of the more complicated models, and the development often went into the domain of simplification, because it turns out that this model, the Rescal model, is a little bit too expressive, so it tends to overfit sometimes. So I think if you understand this one, it's going to be easy for you to learn other ones, and so that's why I decided to explain this model today, and we're going to code it up. And if you want to implement new models, you're going to be easily able to do so. So that is the new objective that we're going to be optimizing for every triple. Or rather, that is how we obtain a score for the triple in this model. And that is all there is to it. We just need to understand what it means. So the score for the triple H, like head, relation, and a tail, is just given by this bilinear form. So we're taking a matrix for every relation. So every relation has a matrix, and essentially this matrix needs to project our entity vectors into a subspace that is representing this specific relation. So, like in the simplest example, imagine that you have a big vector, right, for two entities, and you're just saying that, okay, my first half of this vector represents the relation likes, and the second part represents the relation hates. And essentially, you could just discard half of your vector if you're thinking about the relation likes or hates. At the same time, of course, because of the distributed manner of the representation, most likely all of the information is somehow encoded in all of the components of the vectors. But still, this idea of, I think it's still useful to think of this matrix as, focusing your attention on the elements of the space where a relation is living in a way. Not sure if that was clear enough. I wish there was no delay so I could see you nodding or not. The key takeaway is that this matrix represents the space in which the relation operates, and it's going to be projecting our vectors into this subspace. So in case you forgot what a quadratic form is, this is just a standard matrix multiplication. So you have, let me try to show you how it works in a simple example. Maybe we could just draw a few matrices. Just 1 second. Trying to connect to my device. For some reason my tablet decided to not show you what I want to show. Okay, so you should be seeing it now. All right, so let's say if we're speaking about a 2D example, so H is a 2D vector, something like this, 0, 1. Tail could also be a 2D, it should be a 2D vector as well, could be 1, 0, or, those are actually some real numbers, 0.5, minus 0.5, something like this. And M, in this case, is going to be a 2x2 matrix. So it could be something like 0.5, 0.3, 3, minus 2, for example. So, well, actually, I think I have it written somewhere. Maybe I could just scroll. Yeah, so here's the example with the simple 2x2 matrix multiplication. In the interest of time, let's just take a look at it. So so let me write it down again. So this is head, this is matrix MR, and this is tail. So when you multiply those matrices and vectors in this way, you're getting just a single number. So this number can be used as a score for this triple. And what is nice here is that you could just have different matrices for different relations. So you could have the hate matrix that's gonna, when multiplied by those vectors, it's supposed to give you a low number if people don't hate each other, and a high number if people do hate each other. And you could have a like matrix here that is going to do the same thing for likes, for the relation of likes. So this kind of model is kind of expressive. It can capture interactions between different components. So if you write down carefully what you're getting when you're multiplying the matrices in this form, you'll notice that there's a term connecting x1 and y1. So essentially, if both first component of the first vector is big and the first component of the second vector is big, then this that a11 speaks what do I do with the interaction between the first components. A21 parameter, this one, speaks about how do I combine the second component of the first vector and the first component of the second vector, etc. So you could essentially say, make the score big if the first component of the first vector is large, but the second component of the second vector is small, or something along those lines. So essentially, it gives you some flexibility and it allows you to capture interactions between different elements of the vector. And so essentially, again, it gives you quite a lot of flexibility. The reason why this is relevant is that some of the other models actually simplify Rescal and they restrict all relation matrices to be diagonal. And they still work. So as you could imagine, like the matrices of this form have way less variety than the full matrices that we're considering in Rescal. So this is just to give you an idea of how expressive this model is. Well, that was the tiny quadratic form example. And now the question is, how do we train such a model? So there are two main ways. SGD, which is stochastic gradient descent, or it could be tensor decomposition. Today we're going to be focusing on stochastic gradient descent. And the reason is it is a more universal approach. So tensor decomposition methods were developed specifically for this Rescal model. And I think while they are faster, they're also more specific and it's not as easy to code, etc., etc. Let me know in the chat if you heard about stochastic gradient descent. I did not plan to cover it, to be honest, but if you don't know, it's going to be tricky. So please do tell me in the YouTube chat. Yeah, for some reason I think my previous chat didn't reconnect, so hopefully I could see. Could you show me? Other questions?
No.
All right. Yes, I know. Okay, Monish knows. That is nice. All right. So unless, I think I reconnected to the chat. That's nice. So unless you tell me that you don't know sometime very, very soon, I'm gonna proceed as if you do know it. So let's then continue under the assumption that everybody knows a little bit about stochastic gradient descent. So then we need to think about the objectives. So how do we, even though we decided that yes, we're going to train things using the stochastic gradient descent, there's still a question of how do we formalize the objective for the stochastic gradient descent. So there are two options. The first option is to treat every triple as a binary prediction. So we know that our database consists of triples, of statements, and you need to say whether or not this triple holds or not. So this can be formalized using this traditional logistic regression loss, or we could use a margin-based loss. And it seems that in most cases, or in many cases, margin-based loss works a little bit better, and I think it's also a little bit more intuitive. So we're going to work on that one today. So let's write it down and let's try to understand. This is one of the key formulas today, and let's try to decipher it. So we're minimizing all possible parameters. This is the minimum over theta. Then those tau plus and tau minus, they refer to triples. So every tau is just a triple. So tau plus is a true triple, and tau minus is a triple that is actually not true. It's a false corrupted triple. So what we want is that the true triple gets a score that is at least gamma higher than the score for the false triple. So if we rearrange this a little bit, so this term, the last term in this equation, is the score for false corrupted triple, the f r prime h prime t prime, and we are subtracting the f r h t from it, which means that if our score for the true triple is higher, we're gonna go below 0, right? And if we go below 0 enough, at least gamma below 0, then we're getting a 0 loss for this example. So essentially we're just saying that there should be a gamma difference between the score for a correct triple and an incorrect triple, and if the difference is large enough, with the correct triple getting higher score, we're getting 0 loss. If the difference is not large enough, then it's linearly increasing with how much of a gap is there between what we should have had and what we have. This is a crucial moment in the presentation, so please, if you don't understand, do ask questions right now. It is super, super important. So I'm gonna give you a minute so you could stare at this equation and think. Well, there's also a 1 minute delay between when I'm talking and when you're replying, so I'm kind of always given a minute delay. So I'm gonna still keep an eye on the chat, but I'm gonna move on further, slowly and cautiously. So there's an important thing about negative examples, and the thing is, by default we don't really have them. So usually in the database we have positive examples that are, Mary likes you, Donald Trump is the president of the United States, things like that. But we usually don't have exhaustive negative examples because it would be really expensive to store. So for example, I don't have, in almost in any database, you won't find explicit example like Celine Dion is not the president of the United States. It's kind of assumed that if the entry is not there, then the triple doesn't hold. But this poses a question of how do we actually obtain negative examples? And the usual practice is just to perturb a positive example and hope that we're getting something negative. So let's say we take a triple, Donald Trump is a president of the United States, and then we perturb either the tail or the head of the relation. So we could change it to, like we could take out Donald Trump and substitute something else. So for example, we could randomly sample an entity and we could get a triple, Celine Dion is a president of the United States. And we're going to use this as one of the negative examples. Similarly, we could substitute another tail. So Donald Trump is and we could substitute something instead of a president of the United States. And there are different ways to do so. The most naive way is just to randomly sample an entity from the knowledge base. So you could have something very difficult to interpret. So for example, you could get a negative triple like Donald Trump is a Celine Dion. That could also happen, and obviously it's not a true statement. So we could use this as an example of triples that we should be getting lower scores for. It is important to say that all of this procedure for generating negative facts operates under the open world assumption. So what it means is that we assume that the unobserved relations mean either no relation or is just a missing entry. And this objective, it just says that if the entry is missing, the score for this entry should be lower than what we observe, than the scores for the entries that we observe. But it doesn't necessarily say that it's 100% wrong. If we're operating in the closed world assumption, it's a little bit different. In this case, the absence of relation means that we're certain that there is no relation, and we could just use any of the absent relations as a negative triple. So now let's try to put it all together. So how do we train under the open world assumption? I'm gonna, by the way, there's gonna be a link to the paper from which this algorithm is taken. It's a nice review paper. I highly recommend it if you want to dig deeper into the topic specifically. So first of all, we have a database of observed facts. We're initializing the entity and relation embeddings, and then we're training in a batch fashion. We're sampling as like some small set of positive facts. We're initializing the batch, like the batch of positive and negative examples to empty sets. Then for every sample positive triple, we're corrupting it in some way or another, and we're adding those corrupted and positive triples to the batch. So then what we're gonna do, we are gonna use this second formula, which is essentially just rewriting what we had before, our objective. So we're gonna calculate this objective on our batch. So you could either take all possible pairs of positive and negative triples. In my implementation that we're gonna go over today, I'm just connecting the triple and its corrupted version. I'm not taking all possible arrangements. I think it's a design choice. And that's it. So you're calculating this loss, you're updating the gradient, and you repeat. So again, it's a good moment to ask questions. Take a moment to look at this algorithm. Just to summarize, we're just taking triples, a batch of triples, we're corrupting them, and then we're plugging the correct and incorrect triples into our function, which is this function that uses the matrices to assign a score to every triple. And we're plugging those scores into our loss function that was discussed earlier, and we obtain the objective that we could optimize. There are different ways about how to exactly optimize it. We're going to use it. We're going to do it using PyTorch, so we don't have to manually compute the derivatives, which is a little lazy, but also very, very fun and very quick. So, all right. I'm giving 1 more minute for you to look at the screen to try to understand this algorithm and ask questions, because we're gonna have a big transition right now from speaking about theory to coding. So it would be nice if you understand what we're gonna code. All right, I hope that you do understand it. I'm still welcoming questions, of course. If you realize later that you don't understand something. And right now I'm going to drop a link to the student version of the code for the knowledge graph embeddings. And we're going to go through it together. That is the plan. All right, here's the link. Let me know if you can or cannot open it. I'm gonna double the link. Hopefully it's the same one, but just in case, use the second one. And let's open the student version and try to go through the code together. So yeah, the next slide was this one. Let's code it up. That's what we're gonna be doing mostly for the remainder of the workshop. There's gonna be tiny additional part at the very end, but let's try to code it up. So hopefully you can see what I'm showing you. Is it readable? Please do let me know. Is it possible to read the code? Or should I make it larger? Okay, I'm being told that it is fine. I'm gonna slightly enlarge it. Hopefully by now it is definitely fine. So, well, first of all, it's of course imports. That is everything that we're gonna need. Okay, looks good. I've been told that it looks good, so that is nice. Not that many libraries, which is probably nice. I'm actually not sure if I ever used the name tuple. I think I wanted to be fancy, and then I never applied it. So NumPy, Torch, itertools is this standard Python library that allows you to elegantly operate with sequences. If you never heard about it, I'm gonna have to explain a few things in my code, but it's not a big deal. And then we are also importing the Torch neural networks module. And of course, we're importing some plotting software as well, or plotting libraries, packages. Set in random seed. This is all standard and simple. Now, next the question, when I was preparing for the workshop, I was faced with the question whether I should take some of the existing knowledge bases or we should do something else. And as you could have guessed, I did something else. The reason is that the concept net is fairly big and also requires a little bit of parsing and handling different types of problems that are not very insightful and are also very specific to different databases that are there. Eventually, you still have to end up with the same thing. You need to end up with a set of triples. So I decided to just generate an artificial database so that it's less noisy, more controlled, and that nobody has trouble loading the data set. So we're going to make a simulated knowledge graph. It's going to be a knowledge graph that in a very simplified way simulates interactions between students, teachers, and their pets. So what we have, if we have students, 500, although this is a parameter that we could change at any time. There are 10 teachers, or there initially were 10 teachers. I think I actually increased this number, and you could easily change it if you want. There are subjects that the teachers can be teaching, which is math. Those subjects are math, computer science, psychology, and art. And there are 250 pets, which can be cats or dogs. And there also is a small number of abstract entities, an entity student, teacher, cat, and dog. So those are essentially, we have actual cats, and then we have abstract entities, like every cat is connected to the abstract entity cat by the relation is a. So yeah, that's why similarly, every student is connected to the abstract entity student using the relation is a, etc. And we have a number of relations. We have a relation likes, we have a relation is a, we have a relation studies, teaches, has a is essentially about pets. We have a relation dates, and lastly the relation hates. And we have a bunch of rules according to which we're constructing the database. So if two students have the same type of pet, they like each other. If two persons have the same pet, so not the same type of pet, but the same exact pet, then they date. If two students study the same subject, there is a certain probability that they like each other and a certain probability that they date. The logic is that, if you study the same subject, most likely you have a high chance of interacting. You also maybe share interests. So that increases the probability of liking each other. If two persons have different types of pet, they hate each other. That is a little bit dramatic, but why not? This is our simulated world. We could make it whatever we want. Next, anybody who studies computer science studies mathematics too. I believe that's how it should be, and I think that's largely how it is. Anybody who studies psychology hates math. So this is a little bit of self-irony. Actually, my first degree is in psychology, so I'm just trolling myself. All teachers teach exactly one subject. Teachers teaching the same subject hate each other. It's rivalry. Everybody thinks that their subject should be taught in a different way. Teachers like and study their subject, and all teachers like their students. So the students that study their subject, the teachers just love it when students attend their lectures and study their subjects. So if people like or hate the same things, there's a probability they're gonna like each other or date each other. So this is this code is technical. We're not gonna rewrite it. It's just a way to create a data set. I don't think there's much sense in going deep into that, because it's not about the knowledge graph embeddings themselves, it's more about how I generated a data set. Well, if you want to, you could look through that, like I provided a link to the code. In short, we're defining this entity class. It has a set of things that are related to every entity. We're generating this knowledge graph. Just first, I'm initializing different entities, and then it's really not very insightful. So I'm just creating entities and then applying the rules that I was speaking about before. If there's something confusing, or if you're interested in this part, just let me know separately. What is important for us is probably here. So we have generated this knowledge graph, which is a list of entities, and then we transformed it into a tensor form. So the way it works, we just have a 3D matrix. So the first dimension is the number of the relation, the second dimension is the number of the entity, and the third dimension is the number of the second entity. So if the tensor of r, j, and k is equal to 1, it means that jth and kth entities are related using the relation r. Otherwise, it's going to be equal to 0. So that is the tensor representation for the knowledge base. And the second thing that is important to know that is we have a set of triples. So the triples are just triples of indices stating our facts. So in most cases, you would kind of start here, right? If you downloaded a database, you need to figure out what is the interface of this database, and you need to somehow convert your representation to either a tensor or the triple form. We also have a helper function. So for some entities, it's nice to know their indices. So, and for relations as well. So we know that the first relation is likes, second relation, so first slice of this tensor corresponds to the relation likes, second slice is the relation is a, etc. And similarly, we know the indices of certain abstract entities. So the total number of entities is fairly small, it's 273. Definitely it can be way higher. Total number of facts is noticeable, but again, not huge. And that's just an example triple. It's just 3 numbers. So let me know if the representation is clear or if it's confusing. And again, if it is confusing in any way, feel free to stop me and ask questions. So now here comes the key part of implementing this kind of model. So let me check the YouTube again, see if there are any questions. I don't see them yet. All right. Well, then I assume that everything is clear so far, and let us proceed. So we're going to be implementing this model using PyTorch, and its functionality is kind of flexible. So if we go back to the algorithm that we have, we need to first initialize the entity and relation embeddings. So we're having this Rescal embedder as a separate class in PyTorch. It gets a number of relations, number of entities, and the embedding size as a parameter. So we save those parameters at first, and then let's think about how do we represent the head embeddings. How do we represent them? One way would be just to simply create a matrix of a size num entities by the embedding size, and then manually pick the embeddings from this tensor when we need them. But at the same time, PyTorch has a special embedding layer. So it's I wish I remember how exactly modus Well, and this is the moment when you could start coding along as well if you like to. Embedding layer. I'm gonna have to peek into my other code, but the key thing is that this embedding layer just gets the number of embeddings and the embedding size as parameters. I don't remember exactly what is the order of arguments there. So let's just peek real quick, see how we implemented it, because thankfully I do have everything coded up. So modules was unnecessary. Yeah, it's just, and then embedding, that is how it is written. So the number of entities is named intuitively. Embedding size is also named intuitively. So it should be clear. So this kind of module, it gets indices of words that you want to get embeddings for. And yeah, I also set it to GPU, but we're not really hitting any big training sizes. So essentially, if you want to stay on CPU, that's fine. So head and tail embeddings are exactly equivalent. The relation embeddings are a little bit tricky, right? Because relation embeddings are essentially a bilinear layer for every relation that we have. And in my opinion, the easiest way to code it up in Torch is to use this functionality of a module list. So we're going to have a single bilinear layer for every relation. So the way we could write it is using list comprehension is like that. All right, so well, we could add self. I think it's considered a slightly better practice. And now we need to provide parameters for this bilinear layer. So we know that the size of both head and tail embeddings is going to be the same. Actually, it's not necessarily true. You could even play around with changing the tail and head embedding sizes to be different. So there's even a hint. So in is the size of the incoming embedding is self-embedding size. The size of out embedding is the same, and then the number of features out is 1 and bias is false. Because as you remember in this Rescal model, there's no bias. We're just multiplying two vectors and that is it. So yeah, it's important to correct this. This simply means that we only output one number. It may be possible, not maybe possible, it is possible to just use one bilinear layer to, output the number of relations every time. But it is going to mean that for every pair of vectors, you're always going to get an answer for all possible relations, and it is a little inefficient. It is easier to write, but I think it does slow down your model quite substantially. So I'm not doing this here. All right, so let's try to code up the forward function. So those are the key ones that we need to really make this model work. So I separated it into two. It's not really necessary. So let's see what is the specification of the forward function. So it just gets a list of tuples in this form, and it wants to return this Rescal model activation for every triple or every tuple. So entities, those H and T, are just indices, and the relation is also an integer. So let's try to code it up. I decided to separate it again, and let's start by coding the forward for one relation. So this is essentially gonna do a slightly different thing. So tuples here could be for different relations, right? So in the first tuple, it could be relation 1, likes. In the second tuple, it could be relation 3, hates, or something like this. And so it makes it a little bit more difficult to use our model structure. So let's first handle a simpler case when we know that there's only one relation and we want to compute the activation, the Rescal model activation for all indices that we have. So this is a direct application of this embedding layer and relation embeddings module. So it should be just a one-liner. So we're going to return right away self relation embeddings of the relation index. Right. So this thing is going to give us the corresponding bilinear layer. Now we need to find the activation of this bilinear layer. By feeding in the head and tail embeddings of the words that we're interested in. And this is also easy to do because head embeddings we're going to get by activating our head embedding layer by providing the H indices. And we also need to provide the tail indices in a similar fashion. And that must do that. That should be enough. That should be enough. So as you see, it's a hopefully clear code for now. Let me know if you're confused about anything. Well, at any times, this message is relevant at any times. If you're confused, please do let me know. Well, in any case, now let's complete the more challenging forward function. So the forward function needs to somehow compute the activation despite the fact that there are different relations involved. So the way we're going to do that is we're going to first make a pre-made matrix for all activations. And what we're going to do with it later is we're going to fill it chunk by chunk. So let's say there are 30 triples. First 3 are relation 1, and also last 3 are relation 1 as well. So at the first pass, we're going to identify where in those triples is each relation. We're going to compute the activation for that part using the forward one relation function that we just completed, and we're going to essentially fill the pre-made vector chunk by chunk, relation by relation. So that is the intuition that we're going to try to implement. Let's try to actually write it down. It's always playing with fire when you code live. It's not that I don't make dumb mistakes when I code by myself, but it's a well-known fact that you make way more dumb mistakes if you code in front of an audience. Well, wait. All right. So let's how we call it, scores. Let's make it to be torch zeros, tensor. We know its length of tuples. Let's keep it let's keep it of this size, because I think there's some kind of issue if you have, well, no, it's hard to explain, but when your model returns an activation, it's gonna return something of a size like n by 1, and if you try to add it to a vector of a size just n and like this flat vector without the second dimension, I think it's gonna complain. So that's why we're keeping this as a matrix of n by 1 as opposed to just a vector of length n. Well, in any case, we need to iterate over relations. How do we do it properly? Let's maybe let's first extract the relation index from every tuple. every tuple. We could do it in the following way. So we know that in every tuple, the relation is in the middle. So we could do it this way in tuples. So this is going to be the array of relations. Or we could maybe make it a torch tensor. I don't think it should matter too much. So now we're going to iterate over all possible relations. Not sure if I need requires grad here or not. Probably do. Well, in any case, for R in this range, we're gonna go over self number of relations so that we are guaranteed to go over all relation indices. Now we need to find all indices of the current relation. So what we're gonna do is we're gonna find those things really quickly using this operation and then the operation where. It's a little bit tricky. I'm almost confused by the Python where and torch where, but the idea is that it must return the indices of the elements where something is non-zero. So that is exactly what we want. Let's actually make it numpy array just for convenience. Maybe it's gonna fail us. Also, I think numpy where returns something. It's like it returns two elements, and the first element probably is not needed. We could peek a little bit. No, we could peek later when it fails to work. In any case, so right now we need the subset of the tuples that represents what we're interested in. So we need the tuples of those indices. So let's do it in a naive way. It could be factorized better. And I think if we actually passed tuples as an numpy array, it would have been much more elegant already. But it should work either way. Well, all right. So let's tuples. Well, let's assume it's an numpy array for now, because otherwise it's very ugly. So now we got tuples that are corresponding to the current relation, and we could also get the current activation or scores is going to be equal to forward self forward one relation of current tuples. And now we just need to add update our accumulating array only incorrect indices. So it should be those. So this should be very similar to what I had before, and I think it should work. There must be some minor typos. We could try to run a few more cells in this one and see what breaks. We also, of course, need to return the scores. Probably doesn't require gradient really. Yeah, this original array probably doesn't need the gradient. Okay, let's see. Oh my god, yeah, I needed to run all cells before that, of course, too. Let's see if it works. Okay, we got some kind of error. Okay, numpy in the array doesn't... Well, then it should be a tensor then, I guess. Or... oh. Yeah, this collab is nice, but sometimes it's a little unpleasant to scroll back and forth. Let's try this. We could also just look it up. I don't think it's very... so it is torch after all. Oh, I see. I rewrote it a little bit differently. I see. Yeah, the thing is, the forward one relation actually expects a list of indices. It doesn't just expect the tuples, so that's why. Well, I think it makes sense to just go through this code. I'm gonna copy paste it. You saw the reasoning, but it's always, of course, there are some small mistakes here and there at all times. That is fine. So let's go through the code, how it is supposed to be. Well, at least how I implemented it a few days ago. So first of all, we're creating this result that it's going to be the accumulator function. It is indeed of the same size we were speaking about. Now, the next thing that I'm doing here is that I'm using zip. Zip is a function that's going to take a list of triples and turn it into 3 lists of individual elements. So we're going to have a list of first elements, the list of second elements, the list of third elements, and then I'm converting this to long tensors because those are really indices, and PyTorch needs to work with its own kinds of tensors, otherwise it may complain in some cases. And then again, we are iterating through all possible relations, so it is torchware, not numpyware. That works too. So yeah, here we're getting the indices of the tuples for the current relation. And yeah, this little thing is gonna help us avoid the mistake when there's no, in our current tuple, there's no elements according to this relation, because this function is not prepared for this kind of thing. But if there are relations in the set of tuples that we're considering, if there's at least one entity, at least one triple that asks about the current relation, then we're going to proceed to obtain the activation for this current relation for all triples. And then we're only updating the indices that are relevant, of course. So we're only updating the result in the spots where the current relation is present. So forward new entity, it's a little bit of an additional function. So currently, as you see, our database is kind of fixed. So we know that there's a number of entities, there's some embedding size, but if I want to introduce a new entity and, do gradient descent for this new entity only, which is something we're maybe going to do towards the end of the workshop, maybe not. But yeah, essentially we need to expand this machinery by somehow providing a new entity embedding manually. And so this forward new entity does exactly that. So there's this new embedding that you could provide, and you could obtain activations by substituting this new embedding instead of a special symbol in those tuples that correspond to this new embedding. Well, we're going to touch on that later. So the forward function is now completed. Let me know if there are questions. I would like to see if you do understand what we just covered or not. Well, also type plus or something if you do understand. That would be nice. Just to make sure that we're on board. Giving you a minute to decide whether you know or not. sorry, to decide whether you understand or not. Well, let's assume that you do. And let's proceed. So we implemented the forward function, which is really the key function for any PyTorch model that you may be interested in. And now it's all about implementing the training part. Also, let's write something like pass here so that we don't get any syntax errors. So let's create the model. Works. And let's go through the optimization code. So I decided not to write it on the spot because it's fairly like it's both simple and technical, and I think it's better to just it's very easy to make a very simple and nasty typo. So let's just go through the code to kind of understand what exactly is going on. So first of all, we're going to take a look at positive predictions. Actually, this function is all about evaluation. It's not the training function. But one of the fancy evaluation metrics that you could do is sorry, I'm jumping a little bit ahead. So this function is actually just computing the loss, but we could use it to, for example, evaluate Rescal on validation set with no gradient, because it's not cool to copy and paste this code many times into our training function. So let's go through it. So this function just computes the loss. So we're getting some positive tuples as an input. We also get the margin, which is this gamma we were speaking about before. This gamma. So positive tuples, the embedder that we're evaluating, and the gamma. So first of all, we're computing the positive predictions. We're just forwarding, in the most straightforward way, we're just running the forward function on the embedder. Then we're constructing the negative batch. So the negative batch is constructed as follows in this case. So as you see, we're taking the previous tuple, HRT, we're discarding the H, and instead of the head, we're substituting a random number. We're just picking a random entity instead of one of the elements of the relation. And this is supposed to give us a negative tuple. That is how that is a standard practice on how to generate a negative example. Then on top of that, we are doing the same thing but with the tail. So for every tuple, we're getting 2 negative examples. So here we're obtaining the activations or the scores for all negative examples in this batch. After that, we're just computing the loss. So since we have 2 negative examples per every positive prediction is going to be used twice in the loss computation. So first of all, we're initializing the loss like that. This is the matrix form of the loss that I was speaking about before. So we're computing element-wise the loss function I was speaking about before. Hopefully it's clear how it happens. So it is exactly mirroring this formula. So we're subtracting positive predictions, which is here. We're adding negative predictions, which is this part. The only tricky part is that we need to match positive predictions with negative predictions, and since we know that there are 2 times as many negative predictions as positive predictions, we're just taking the first half here, doing this, and then doing the same thing for the second half of the negative predictions. It could be, you could go a little fancier. For example, you could match the positive and negative predictions in some other way. It is not prohibited at all. So in the training procedure, we're doing exactly the same things, but now there's an optimizer. So the optimizer is going to optimize over embedder parameters. And one of the convenient things about defining things like that is that all the modules are going to have exactly the parameters you expect them to have. You don't have to manually specify what kind of matrices you need to optimize over. So that is nice. That is nice. PyTorch is very convenient, I'll say. So now for the number of epochs that we're interested in, we're first gonna evaluate everything on the Oh, so here we're computing the training loss on all the training set. We could afford to do that because we have a very small training set. In general, you would usually subsample something here, but since, again, the dataset is small, we could afford to evaluate our training loss on every epoch over all training examples. Then if there is any validation set provided, then without computing the gradient, we're computing the validation loss, and we're just printing those metrics. So this is the simple part, I would say. And again, I think if you saw at least one workshop on stochastic gradient descent, you should recognize this kind of code. It's more or less the same whatever model you're training. Yeah, I'm just essentially copying this code that we went over before, but now it is computed with gradient. It's probably possible to just simplify this and run this function instead. Probably it's a good idea to do so. Well, in any case, we're just sampling a batch. So before every epoch, we're sampling an order in which we're going to be sampling the batches. Then during every epoch, we're just sampling batch by batch and doing exactly what I explained earlier. We're computing the loss, and the key thing is that we're calling this function, which is loss backward, which is going to propagate the loss gradients all the way towards our parameters, and then we could make the optimizer step. So I'm kind of assuming that you know a little bit about PyTorch and a little bit about stochastic gradient descent, because I think it would be a little bit. I said a little bit too many times, but I do think it's going to be a little bit of an overkill if we go into PyTorch right now in depth. So if you don't understand this code, just make sure you check out some tutorial on PyTorch, or you could reach out to me. I'm happy to help. But this part is a very standard implementation of a stochastic gradient descent, and the way we adapted to our model was explained here. So if you're confused, let me know what are the questions. Since I don't see questions, I assume it is more or less clear, which is nice. So now when all of those functions are defined, we could try to train our model, and it is indeed works. So we're seeing that the loss goes down. We're feeling very happy about it. What is left is to evaluate the Rescal in some more meaningful way than just looking at the loss. So one of the common metrics for evaluation is the mean rank. So imagine you have a triple, like A related to something. So A is known, relation is known, but the tail is not known. Or like head is known, relation is known, tail is not known. And now you're scoring all the possible triples according to your score, and you're looking for the rank of the tail, of the correct tail in your scored list. So essentially, let's say you have a beginning of a triple, an apple is, and then you're scoring all possible tails. So you're gonna evaluate the triple. Apple is banana. Apple is I don't know, cat. And then there's also gonna be triple. Apple is a fruit, right? And so you would hope that this apple is a fruit is going to be higher in your score than apple is a banana. And so if you just compute the scores for all possible triples, sort them according to the score, and you could take a look at the rank of the correct tail in this list. And this is going to be the mean rank metric for triple completion. And that's the metric I implemented here. I think it is fairly straightforward, and it's also very technical. It's not about the model, it's just about how to compute those, the ranks of the triples. So I'm not going deep into detail here. if you want to check this function in more detail, and if it's somehow unclear, let me know. There's really nothing fancy. But again, if you never worked with arcsort is a function that always gets me. I somehow have to play with it separately before it works, almost always. But yeah, that's the function that we rely upon to compute this mean rank. So we're predicting everything, we're then using arcsort to get the indices of different entities, etc., etc. So we're still waiting for the training to complete. It should be done soon. And I think you could trust me that those metrics are indeed computed. I would like to again take a small break, small pause for you to ask questions. If everything is unclear, please do ask me. And we're moving towards the conclusion of this workshop. So I had a separate section on, like in case we were to move faster than we did. I wanted to speak a little bit about the extension of this basic knowledge graph embedding technique. So what we have right now is that we have a static database, and by training this Rescal model, we could obtain an embedding for every vector. What is cool about it is that you could pass those vectors, you could reuse them in a neural network, for example. You could do inference. You could predict new triples that were not in your database, but that are kind of consistent with the structure of your database. But what you cannot do by default is to infer new entities. So for example, you have a database of teachers and students, and now you want to introduce a new teacher into your database. You're saying, okay, this teacher, let's say, teaches computer science. It likes such and such people. It has, let's say, a cat. What are the likely implications? Who else is this teacher going to like, etc.? Because our database has a very specific structure, right? So if the teacher teaches computer science, we would expect this teacher to like computer science students, right, according to this rule. And we would also expect this teacher to hate other computer science teachers, because that's how we defined the database. So in order to do so, we need to somehow learn a new embedding for this teacher, and preferably do so from just a few attempts. We don't have time to go into that, but the idea that is implemented, that I implemented here, is that you could actually initialize a new embedding and just run gradient descent a few times to optimize this one particular vector. So that is a very naive approach, but it may work to an extent. So what I found while experimenting with this particular setting, though, is that it doesn't generalize as well as you would like it to. And there are many reasons for that. So for example, if you would expect the model to generalize in the following way. You're saying nothing about a new entity other than this is a CS teacher, right? And since we know that all CS teachers hate all other CS teachers, we would expect the model to generalize based on that. But the model is not always working as you expect it to work. So while the model can rely on the fact that something is a teacher, it could also rely simply on the connectivity structures between people who hate each other. So, if there are 10 people, there are total 10 CS teachers, and they all hate each other, right? And so what happens is that you don't really need to check whether they're CS teachers or not. We just know if there are 10 incoming hate connections, you're gonna reciprocate and just spread out those 10 connections back. And so while the database may have a very clear logical structure, the generalization in the model itself may be based simply on similarity in clustering, as opposed to inferring the logical rules. So my point is that the gradient descent based optimization, item-based optimization may not really give you the generalizations you would like to have. And this brings us to the project I would like to propose, and I would like you to join if you're interested. So I am looking for students. And the idea of that project is to focus on more fancy ways of inferring embeddings in a few-shot manner, or even correcting the whole database based on new incoming information. So the project aims to combine natural language processing and knowledge graph embeddings to achieve a more flexible knowledge representation. So the current approach I'm working on is to represent a knowledge graph using a large memory layer, which is a fairly recent model, and I think it's a very promising one. So this large memory layer essentially allows you to have a very high capacity memory storage and a very flexible one. So what I'm trying to do is to train a separate network that is going to update this knowledge representation to reflect new facts that are being introduced. So the key idea is that I'm trying to separate the knowledge representation from the ability to access and modify this knowledge. So there's quite a lot of work on trying to augment neural networks with some way of access to a database. So by, for example, feeding knowledge graph embeddings as an input, or maybe somehow attending over a knowledge base. But there's, I don't think there's enough attempts for a more integrated system that would both update the knowledge graph representation, like the current state of knowledge, and refer to this knowledge to answer questions. So I would say a very simple, ideal interaction that we would like to get with the system, and naturally get, not just like hard-coded and do it in a template-based fashion, is something like Agent 1, which could be human, could ask, like, is Obama the president of United States? The model answers yes, because, for example, it may have been trained on the outdated knowledge graph. Agent 1 corrects the model, and the model accordingly updates its knowledge. Another simple interaction that I would like to see as a result of this project is inferring information that is stated indirectly. So, for example, Agent 1 could say, my cat got pregnant, and the updated knowledge graph, and the knowledge graph gets updated that to reflect the information that Agent 1 has a cat, and this cat is female, and this cat is pregnant. And so later this information can be reused in subsequent dialogues. So essentially I'm trying to, as I said, implement this key idea of separating knowledge from the ability to access and update this knowledge. And if you're interested in joining the project and listening, or like maybe getting more details about it, please do contact me. I'll be happy to discuss it. We'll be happy to work with you. Let me check if there are some important messages, maybe some questions somewhere. I don't see questions yet. All right. So with that being said, I think we're reaching the end of the workshop. Despite some technical difficulties, I think we did well adjusting to the circumstances. I hope that the presentation was clear. Again, if you're confused about some parts, please do reach out by email or any other means of communication. So that was an interesting experience. It was a fun experience, and I hope it was useful for you. And with that being said, I say bye for now. I'm gonna chill for 5 more minutes to wait for questions if you have some. And after that, I'm gonna wrap up if there are no such questions. So thank you for your attention. Say again?
Somebody's in the YouTube chat.
I hope to work with you on your project. Not really a question, but I would really like to learn more about your project. Duncan, that sounds cool. We should just maybe text me on Facebook. We could discuss that. That would be nice. you are definitely most welcome. Okay. So I think if there are no more questions, I'm gonna be wrapping up the stream soon. Let's just wait a little bit more. All right. So probably let's wrap it up. So thank you again. Thank you again for your attention. Thank you for staying with us in those non-standard coronavirus times. I hope everybody stays healthy and well. And see you around on the next workshops. So, peace. And have a good rest of the day. And bye for now.